we ran 500 hours at full load, and the engine would alternate between peak horsepower and peak torque for 500 hours straight. You just left it on the dyno running. And if it didn't pass that, the design was not good enough.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we're joined by DeWayne Logan from Ilmor. DeWayne is involved in the design and development of engines, including Ilmor's Indycar engines, which are a 2.2-litre twin-turbocharged V6, producing upwards of 700 horsepower. In this interview, we dive deep into DeWayne's background, how he actually learned the skills of engine design and engine development. We'll talk about the degrees that he took. We'll talk about his practical experience and how ultimately he got his dream job at Ilmor. We'll also go over the history of Ilmor, really interesting company involved, as I've mentioned already, in the likes of IndyCar, also NASCAR, as well as previously Formula One. A lot of interesting takeaways in this discussion, and we don't often get to sit down with someone that is working at the level DeWayne is in engine development. In particular, we talk about the relationship between compression ratio, fuel octane, and boost pressure, essentially how we should go about selecting the correct compression ratio for a given engine. We also talk about the terms knock, detonation, pre-ignition, and superknock. Find out what these are, how they differ, and how they affect the operation of our engine, and most importantly, durability. Speaking of durability, we also talk about the process the designers at Ilmor go through in order to make sure that an engine can produce 700 plus horsepower, running 220 plus mile an hour at close to wide open throttle for 500 miles, which is exactly what they have to do at the likes of the Indy 500. Now, before we jump into our chat with DeWayne, for those who are fresh to the Tuned In podcast, High Performance Academy is an online training school. We specialize in teaching people how to build reliable engines. We teach people how to tune, how to build wiring harnesses. We also cover race driver education, race car setup, data analysis, and fabrication. You can find all of our courses at hpacademy.com/courses, but of specific relevance to our chat today with DeWayne on engine building is our suite of engine building courses. This includes our Engine Building Fundamentals course, which will teach you the fundamentals of engine building. You'll learn how the engine operates. You'll learn the key elements that go into machining an engine ready for a performance build so that you can speak the same language as your engine machinist. You'll learn about the clearances and tolerances inside the engine, and you'll also learn how some of these may need to be adjusted when we're building an engine that's designed to produce significantly more power or rev to a significantly higher RPM range than what the factory intended. Moving on from this, we also have our practical engine building course. This builds on what you learn in the fundamentals course, but this time teaches you the actual process of building an engine. And we know that when you get your pallet of parts back from the engine machinist, it can be a little daunting knowing what to do first and what order to progress in. Well, we've broken this down into the HPA 10-step engine building process. By doing this, each of the individual steps of that process is quick and easy to complete. In no time, you've got to the end, you've got a completely built engine. You're going to have the confidence that every part, every clearance inside that engine is correct for your specific application, and you're going to have the confidence that when it comes time to start it for the first time, it's going to deliver the power and torque you're expecting with, most importantly, great engine reliability. Now, this course is generic. It's suitable irrespective of what type of engine you're personally building. And further on in the course, we also have a library of worked examples, which is where you can watch that 10-step process being applied from start to finish on a real engine building job. Now, as a podcast listener, you can also use the coupon code podcast75, and that will get you $75 off the purchase of your very first HPA course. We'll put a link to that coupon code as well as those two courses in the show notes to make it nice and easy for you to find. All right, enough with our introduction. Let's get into our interview now. All right, welcome along to the podcast, DeWayne. Thank you very much for joining us. And As we always do with every guest, let's get started by learning a little bit about your background and how specifically you got interested in the automotive industry.
Okay, so I think like most of us, I was a gearhead. That's what we call it in the States, at least. I liked to work on cars with my dad when I was young. And then I always had a little bit of a knack for engineering, physics, and math. Actually, I originally planned on being a physicist. I was going to go and do theoretical physics. But then when I realized that it was mostly begging for money from donors, I decided to get into engineering and actually make something. So I got my engineering degree at Northern Illinois University. It's in the US in Illinois near Chicago. Then eventually, after I started working, I was fortunate enough that a job paid for me to get my master's degree. So I got my master's degree in combustion. It's a mechanical engineering degree from University of Michigan. It's near Detroit. So Detroit's got a very big automotive like education and a lot of automotive engineers around there.
Okay, let's get a bit more into this education side of things. So the undergraduate degree in engineering. So engineering in and of itself is a pretty broad spectrum of skills and disciplines. So what was that sort of geared towards specifically? What were you learning in there that sort of carried across to your interest in engine development?
So it was a mechanical engineering degree. I originally wanted to design engines, and I did do that in my career eventually. And I focused on actual control theory when I took that undergraduate degree. You could kind of choose vague specializations. In the US here, they don't really do, you're not going to take a really, really specific undergraduate degree. That's more for graduate school. But I did specialize in control theory for that. And so I think that set me up pretty well to get into the advanced controls area.
Okay, so then moving on to this postgraduate degree in combustion. So that, again, very, very specific. Can you expand a little bit on what's actually involved in that? What are you sort of learning about? What are you studying?
So it's very fortunate here near Detroit that the automotive industry is so big. University of Michigan offered a degree where I could take the vast majority of my classes in automotive design. So you can take engine design classes. So I specifically took 2 combustion design classes where you focus on detailed concepts on how to design an engine from scratch. I took a transmission design class. I took a lot of thermodynamics because that's really the foundation of what you're doing there. Obviously, your standard, math and physics classes, but it was very cool. I got to study all the old masters from the 70s and 80s when they really kind of figured this whole thing out. And it was really interesting. And some of my professors actually were ex-industry who had designed some very high-end, interesting things.
Okay, so at this stage, you sort of come out essentially, I guess we could call you a rocket scientist. I'm interested though, just in terms of engine development, and this is sort of a higher level. At engine development over the years, you mentioned you sort of were studying from some of the previous masters when they started figuring things out. How much of what has been learned about engines has developed, that combustion process has developed over the last sort of 20, 30, 40 years? How much more advanced have we got in our understanding of what's going on inside the combustion chamber?
So I think every burgeoning engine design or even calibration guy, a tuner, should buy Haywood's book. He's kind of the original master of combustion. His book is sort of the Bible. Haywood's the man. So we actually haven't moved on that far from that. What's really happened is that we've gotten a lot more precise with our test equipment to get much better measurements than he was ever capable of. And then our CFD. So the way that we can model combustion processes inside the chamber. So we're capable of doing time-dependent CFD. You can model an entire cycle, frame by frame, essentially, degree by degree of the engine, the crankshaft rotation. It takes an incredibly long amount of time, and it's very, very difficult to set up. But those sort of advancements give data that he just didn't have access to. So I think the fundamental concepts haven't changed. We're just, it's the difference between someone with a film camera and a digital camera.
Yeah, sure. Technology obviously has come a long way, as has the increase in computing power. So that kind of goes without saying. But I guess that it's good to know nothing in terms of the fundamentals of the engine design really have changed. The understanding and the ability to model these more accurately obviously has, though. Let's get back into sort of your career path. So you've obviously gone with a very specific direction with your degree and your postgraduate degree. So are you always sort of looking for a route into motorsport in terms of engine design and development? What were you sort of thinking as you're going through these degrees?
I dreamed of working for a company like Ilmor. The hard part is it's very difficult in motorsport to get to the point where your career isn't holding you back. And I don't mean any disrespect to the aftermarket, but if you want to be on the cutting edge, it's just very difficult to get that sort of experience in racing. Whereas if you work in the OEM, like you work for a Ford or you work for a Mercedes, something like that, they have access to the sort of test equipment and tools and budgets that you just don't see, even in high-end motorsport. So originally, after I finished even my undergraduate degree, my goal was to work at an OEM. I wanted to get that experience, get access to the tools to really become proficient at engine design. You know, a new base engine design, like say Mercedes today, they go, we're going to design a new engine from scratch. That can be $500 to $700 million, no problem. So you just get access to things you wouldn't have access to normally, right? You know, that's several seasons of F1, right? So that was my original thought, because working on motorsport at that level just seemed impossible.
I'm interested the direction and I guess the design constraints for an OE developing a new ground up engine with, you could call it a clean sheet of paper, but really it's not a clean sheet of paper, because they have so many factors driving that design. Primarily, I'm guessing in terms of their emissions compliance, which is becoming increasingly more stringent year by year, versus developing an engine for purely motorsports. They seem to me to be very, very almost opposed. Am I right here, or is the appeal still the same for an OE design from your perspective?
I think if you would have asked me a decade ago, you would have been right. There's been a huge ramp up recently, I think, from the OEM side. They're becoming very cutting edge now with the materials that they're using, with the techniques that they're using. And you're starting to see OEM engines look a lot more like race engines. For example, kind of the holy grail right now in terms of the best OEM like production combustion design is the Mercedes M139. You can see that in like your A45 AMG. It's like their little 2-liter turbo 4-cylinder. That engine is off the charts incredible. It's an incredible combustion design. And you start to see the crossover with motorsport. You start to wonder, did Mercedes take some of the things that they learned from F1 and apply it to that engine? You know, they're getting 460 horsepower out of it now. It's incredible. So I think it used to be a little bit boring instead in like the 90s, early 2000s with OEM development, but there's so much to lose on their front. You know, if you do a poor engine design, they have so much to lose that they're starting to hire smarter people, pay for better tools, and treat it like a more important part of the process.
Okay. Yeah, that makes sense. Yeah, at a higher level there as well, you've sort of talked about the combustion process a number of times, and obviously that was a big part of your education as well. I guess at a high level, what separates an exceptional engine like that Mercedes engine that you just mentioned from one that is just a run-of-the-mill? You know, where do the differences lie in the designs from your perspective?
That engine, I mean, the main measure is BMEP. So that engine, I don't remember the number exactly off my head, but it's something like 32 bar BMEP. I mean, you can think of that in terms of torque, right? So the engine makes, I think, 380 or 390 foot-pounds of torque, and it's only 2 liters. And it can do that on regular fuel that you can buy anywhere in the world. And when an OEM puts out an engine like that, it can do that all the time. Like, they're not going to put that engine out into the world like on the cutting edge. Like, they're not going to tune that up for like a glory pull. You see what I'm saying? When they say it makes 460 horsepower, it does that for its entire life.
Yeah, and I think, if you look at that number, 460 horsepower from a 2-litre turbocharged engine is good in terms of even aftermarket modified engines. But I mean, these days there's people punching out 600 plus horsepower, but the ability to do that all day long for 100,000 plus miles is what separates a modified street car engine from, as you say, a production engine, where this has not been tuned on the absolute ragged edge. It's going to be reliable. The parts aren't going to fall to pieces because, of course, Mercedes need to offer a warranty on the engine, correct?
Yes. One of the engine projects I worked on, just to give you an example of what they do, the commissioning test, essentially the test that determined if the design was sufficient to move on to like your pre-production phase, we ran 500 hours at full load, and the engine would alternate between peak horsepower and peak torque for 500 hours straight. You just left it on the dyno running. And if it didn't pass that, the design was not good enough.
That is a very, very hard test, no doubt. And I don't think too many in the aftermarket would be wanting to test their engine in that sort of a harsh environment. I want to just come back to that term you mentioned, BMEP, brake mean effective pressure. Can you expand on what that is? Because we hear this term and a lot of people might not understand what it actually means and how it can be used to compare one engine to another.
So essentially what you're talking about is it's a brake specific torque. You're talking about, we quote it in terms of bar, which is, like a pressure number inside of the cylinder, but maybe that's not even the best term for a non-engineer to use. You could just do it in terms of torque per liter, I think is the right way to think of it.
So it essentially normalizes the torque output of the engine. So you can compare something on a 3-cylinder 1-litre engine, for example, and compare that to a 5-litre V12, and you can kind of get a comparative value for how good a particular engine is.
Exactly. Yeah, exactly. And from an engine design standpoint, torque is usually more difficult to deal with than horsepower. Your challenge with horsepower is generally revs. So can you make the valve train live to rev high enough to make whatever power number you want to make? But torque's defined by cylinder pressure, and the higher the cylinder pressure, the harder it is on parts.
Yeah, definitely. I mean, we see this as well with, to go off on a bit of a tangent, but I mean, previously I've spoken to the likes of Mountain Tune about their World Rallycross engines, and specifically they don't make huge power. And again, I think the numbers are in the region of 600 horsepower, but they're running sort of 4-bar boost pressure down at sort of 4,000 RPM. So the actual cylinder pressure down at low RPM is incredibly high, and that's what's hard on the engines relative to their actual, what I wouldn't say it's a modest power level, but 600 horsepower from a 4-cylinder 2-litre engine isn't exceptional. So is that sort of what we're talking about here in terms of torque versus horsepower?
Yes, exactly. It's precisely what we're talking about. I wouldn't say it's easy to design an engine that makes a big power number at high RPM, but in general, it's definitely easier from a calibration standpoint, and it's easier from a combustion design standpoint to design an engine that makes lower torque but higher horsepower than it is to make a high torque engine. For example, diesel combustion design is insane. You basically have to be an Einstein now to do it. It's crazy.
Let's sort of expand on this relationship between torque and horsepower, because I know it is relatively simple and relatively straightforward, but it can be really confusing for those who are a little bit fresh to it. So, we've got a formula for horsepower, and we'll talk in imperial units here, but we take our torque, multiply that by our RPM, and then divide it by a constant, which is 5,252. And if you're looking at a dyno sheet in horsepower and pound-foot of torque, that's why the two will always cross at that 5,252 RPM point. But that relationship is sort of hard for people to get their head around. In particular, can we talk about what we need to do if we're talking about a very, very high horsepower engine that also needs to rev to very high levels, or I guess probably to flip that on its head, how we can take advantage of using very high RPM levels in order to get high horsepower levels?
Yeah, I mean, like you said, it's a constant. So you're just you can think of it really simply as your torque times your RPM. So if you're having trouble creating more cylinder pressure, you're breaking connecting rods, or you're ruining bearings or anything like that, the only way to go higher in horsepower would be to make that torque at a higher RPM. So I think the ultimate version of this would be everyone's favorite sound on the planet, those F1 V10s from the 90s and early 2000s. They sounded incredible, but those engines didn't make very much torque. They were only making like 260 to 270 foot-pounds, which is what, not even 400 Newton meters, but they were making 1,000 horsepower. And it's because they made that torque value at 18,000 RPM. So it sounds like an easy button to hit. It's just the problem is making your engine live up there. So the valve train is very difficult to design to live up there.
I mean, it's just two very separate reliability issues, isn't it? You've got the high cylinder pressure of a high torque, low RPM engine. So that's one design concern or consideration. And then, as you mentioned, in order to make very high horsepower, very high RPM, it's all of the other things that go into making that engine hold together and be reliable at, in this case, as you mentioned, 18,000 RPM. And that, of course, is not as simple as it may sound. Coming back to the Mercedes engine that you just used as your reference there. So, the numbers you quoted, as I mentioned, we can achieve this in the aftermarket, but one of the things that becomes problematic in the aftermarket is, in order to make high horsepower, generally we'll try and move towards a better grade of fuel with a higher octane that's going to be less susceptible to knock detonation, maybe E85, for example, or at least the highest octane pump gasoline that we've got available to. So that allows us to use more ignition timing, more boost, or potentially a combination of both. Now that'll get us so far, and then also we go with larger turbochargers, which kind of help make more power, but generally the downside with that is we trade off that boost response. The low RPM boost response is nothing like we'd see from a factory engine. So when we take those elements into consideration, the fact that Mercedes are able to make that sort of power with, I haven't driven the engine, but I can only imagine with exceptionally low boost thresholds, really good boost response on an engine that is able to run on lower grades of fuel. That's really where the win comes from. And I'm just interested, in terms of being able to get very high cylinder pressures, low RPM without knock occurring, or without knock being such an issue, what are the design considerations that go into making the engine less prone to knock? Really, that's the question there. It's a long-winded way of getting there.
So what you're looking for is mixing inside the cylinder. Like a modern dual overhead cam 4-cylinder turbocharged engine like that, you're going to be looking for really high tumble inside the cylinder. And you're also going to be looking for very short burn times. You essentially, from the time you fire the spark plug, you want to get to, like, say 50% mass burn fraction, like your AI50. You want that to be very, very fast. So you can think of like a common aftermarket engine, like a 4G63, your Mitsubishi 2-liter 4-cylinder. If you look at one of those, or a Honda B series, the ports are designed, you essentially have very high valve angles. So they call it like a pent roof chamber. Your valves are at a steep angle relative to the piston. That way you can fit big valves, and then you can have a very straight port that flows a lot of air. When you're trying to make as much power as you can and you're knock limited, like on octane, your strategy completely changes. You stop worrying about airflow and you start worrying about mixing, right? So that Mercedes engine probably doesn't flow as much air as even like an old 4G63. What they're doing is, you make the cylinder head able to deal with as much cylinder pressure as possible, and then you make up for that lack of airflow by just pounding boost through it. I mean, they're probably running, it wouldn't surprise me if they're running 3-bar boost to make that number. And how they do that with cylinder heads is they're going to have very shallow valve angles. The valves are going to be almost flat relative to the piston top, almost like a diesel. And then your port will actually be at a pretty steep angle relative to the valve. It's difficult to actually think of in your head, but what they're actually trying to do is they're trying to create a low pressure area when the air comes inside the cylinder, and it makes it spin. It makes it spin really, really fast. It's not quite that simple. It's very involved, but they run small bores. I think that engine's only 81 millimeters, something like that. It's very small bore. So you stop focusing on airflow, which is what the aftermarket tends to do, and you start focusing on making it as knock resistant as possible. And then if you want to hit a certain fuel flow, certain torque number, you just keep cranking up the boost. And so I think a lot of people get caught up in, okay, I made 600 horsepower on only 15 pounds of boost. They don't focus on that anymore. They say, I made 600 horsepower on 91 octane fuel or 90 RON fuel.
Yeah, and that's if anything, definitely a bigger challenge. Okay, interesting to get some sort of concept around what goes into one of these more modern cylinder head designs. And I think just to sort of go off on another bit of a tangent there, you mentioned the boost pressure that Mercedes are potentially using. I mean, you're quoting a number there that may not quite be accurate, but let's just take that for an example. What I wanted to get at here is a lot of people, I think, in the aftermarket focus too much on a boost pressure number, and without really understanding that the correlation between the boost pressure number and the airflow is not necessarily sort of a linear correlation. What I'm getting at here is boost pressure really, in terms of engine power and engine reliability, is not the be all and end all. What we need to understand is the airflow into the engine, and so many other elements that come into play here. Like you mentioned, the modern Mercedes cylinder head probably, for all intents and purposes, won't flow as well as an old 4G63. So that's where you need to use more boost to actually get that air into the combustion chamber, and that's the part that's going to make the pressure in the cylinder, and hence our power and torque. I just think that's so often overlooked, and people focus too much on the boost pressure number, which, without everything else is really of very little relevance. Coming back to what you were mentioning, though, that the getting that tumble of the air, that's part of the process. I guess the other one is how the fuel's introduced. Obviously, it's been a long time since we've had production port injected engines. Everything's moved to direct injection. Is there an advantage in the way the fuel is introduced as well, which sort of plays into this, or are the two sort of completely separate?
Oh, there's definitely an advantage. You'd be surprised when you're setting up a DI engine, when you're doing calibration on it. I've seen 10% torque increases by messing with injection timing. It's pretty incredible. Most of the time they're going to be looking to maximize brake-specific fuel consumption because that's what the OEMs are concerned with. But you can also move injection timing to cool specific components. Like, for example, if you want to cool the top of your piston, you might inject the fuel earlier when it's at top dead center, right? Or if you're trying to cool a valve, you might start injecting the fuel a little bit too early and let some raw fuel go out the exhaust, but it may cool the exhaust valve. That would be more of a performance application. You can do some things with DI that you just can't do with port injection.
Yeah, of course. And what we also see is the shape of the piston crown on a direct injected engine is quite unique compared to a port injected engine, because it's being, as I understand it, being used to sort of help direct the fuel as it's being delivered from the injector. Is that correct?
Yeah, and also those new piston crowns they use, it helps the air as well. So you're helping the tumble. You see this most clearly in diesel design, where the piston looks like a combustion chamber almost. It's this bowl. And they've taken some lessons from diesel design now and applied it to GDI combustion.
Now, another element we see in some cylinder head designs is sort of, as a variety of names they're referred to, sort of squish pads or squish area, basically sort of a flat area on the extremities of the cylinder head, which will come, or the piston will end up coming very close to those areas. And as I sort of explain or understand it, it's kind of designed to try and help move the fuel air charge inwards towards the spark plug to help make the engine less prone to detonation. Now, in the aftermarket, there's as many people keeping those areas in the combustion chamber as there are them removing it. Have you got any sort of insight you can share with us on that aspect of the combustion chamber design?
Yeah, they're not quite as common now as they used to be. They tend to create charge motion now using other techniques like cylinder head design. That squish area is an older method to help charge motion, essentially, to get the mixing that you want. Essentially, if you're working with any engine that was designed after the year 2000, I would say, those factory engineers knew what they were doing. I mean, that's not necessarily always true, but as a blanket statement, I would say most of the time you're going to make it worse if you start removing significant parts of a cylinder head from an OEM design. There's usually a choice that they made there, particularly on any machine surface. If you see a machine surface in the head, that costs money. So they didn't do that unless they absolutely had to.
All right, we've gone kind of down a bit of a rabbit hole here, which has been really interesting. Let's sort of come back to your career, and you're currently working at Ilmor. I'm just interested in learning about the trajectory of your career to get you to Ilmor. Did you sort of step straight out of university into that job, or have there been other things that have sort of gone on between?
Actually, it's COVID, man. So I was working at another job, ABL. They're one of those consultancy services I talked about. I think everyone kind of fell on hard times in 2020. And I had to make some career choices at that particular point. The opportunity came up to move to Ilmor, and Ilmor is surprisingly COVID proof, I guess is the right way to put it. They were doing quite well in 2020. And so they made me an offer and I made the jump.
Excellent. In terms of others who are maybe sort of in a similar position to you in terms of knowledge, experience, education, I mean, is it a case of, just rocking up to Ilmor with your resume and applying for a position, or do you kind of really need to have the secret handshake or be introduced by someone already in the know to kind of get your face in the right place?
I'd say try. I mean, that's the best thing, right? Just give it a shot. I actually applied on motorsportjobs.com. They have a website that's just got a whole bunch of motorsport jobs. Pretty cool website. And that's where I applied, but I've seen them on LinkedIn. I think you just got to go for it. We do hire a decent number of young people that aren't super experienced. So I think even if you don't have experience, and this goes for any cool job, Red Bull, F1, or if you're working, all over the world, I think you got to you try, right? The interview process was brutal. I think I went through like 4 or 5 interviews and I didn't really think I was going to get the job. I think it's just one of those things. Sometimes you get lucky, right?
Absolutely. Oh, and I think you make your own luck as well. Obviously, you've got the runs on the board to get to that position in the first place. So probably maybe need to give yourself a little bit more credit there. For those who maybe haven't heard the name Ilmor, let's get a bit of a sort of high level view of their history. Can you kind of fill us in on what the company is, how it was formed, and what it is today?
Yeah, so there were a couple engineers at Cosworth actually in the early 80s, and Mario Ilian and Paul Morgan, and they decided that they thought they could do a better job, I guess, than Cosworth. And so they started their own company and decided to design an Indycar engine. So their first Indycar engine was, I believe, in 1983. Don't quote me on that. But it was pretty interesting, and they did well. I've met Mario. He's still involved with the company, and he's an extremely intelligent engineer. He lives in Switzerland, actually, I believe. So he comes over and visits every once in a while to the U.S. facility. And, from there, they just kept moving. They've done F1. So they did some early 90s, I believe, Jordan F1, and then the wins with, what was that, 98 and 99 with Mika Hakkinen. Those were Ilmor involvement. So they've done F1. We've done MotoGP. We do NASCAR. We currently supply I shouldn't say all, but most of the NASCAR truck engines. We do the ARCA series, which is sort of like, if you could imagine, it's like Formula 2. It's like the feeder series for NASCAR. And obviously IndyCar. IndyCar is their biggest thing. They've been doing that since 1983 consistently. We've always been competing in IndyCar.
In terms of the F1 side of the operation, as I understand it, that no longer exists, was bought out. Is that correct?
Yeah, I wasn't around for that, so I don't know all the details of what went on there. But at one point, Mercedes actually owned all of Ilmor, so I don't know exactly what went down with how that happened. But eventually, Mercedes just kind of, took the F1 part as their own, and I think it was a partnership all the way through. But like I said, I wasn't around for any of that, so I don't know exactly how that went down.
Fair enough. In terms of the facility at the moment, what's the size and sort of number of staff in the US?
It's about I don't remember off the top of my, I think it's like 130, 140 people. It's something like that. So it's not huge. Then we also have a facility in the UK in Brixworth that I believe is smaller. I don't remember the numbers off the top of my head. Yeah, Ilmor's not huge. We're not like some giant, 1,000-person company or anything like that. I don't think most motorsport operations are.
No. I mean, it is a very niche industry, even if you are working at the top levels. I mean, could you give us a rough ballpark of, number of engines that are being produced per year?
Yeah, I think I could do that. I think we do over 200 NASCAR ARCA V8s a year. And as far as IndyCar engines go, I don't want to be misquoted here on this number, but I believe, because essentially you'll do rebuilds as well. So it's not just new engines, but I want to say including rebuilds, we do right around 100 engines a year, but I could be a little off on that.
All right, let's dive a little bit further into Ilmor's involvement with IndyCar. As you sort of mentioned, maybe sort of circa 1983 got involved. And as I understand it, we're sort of partnered there with Chevrolet in the development of what was a V8 engine at the time. Moving forward, can you start with what is the current engine formula for IndyCar? What are we looking at?
It's a 2.2 liter V6, and that's dictated by IndyCar. They've created essentially a very stringent set of rules to kind of keep an even playing field.
How much flexibility is there beyond the fact that the capacity and the number of cylinders is fixed? Have you got flexibility in terms of the engine architecture, bore and stroke, for example? What other kind of limitations are there around what you can and can't do?
There's some flexibility. Mostly the way they dictate it is with the rev limit. So they're limited to 12,000 RPM. They have a over rev capability, which is like a push to pass sort of thing, I guess. And then it can go to 12,500 RPM. But when you're looking at designing an engine and you're limited on, your boost pressure and your RPM, the engine almost designs itself. So in theory, yeah, I guess there's some variation there, but the engines end up looking quite similar, I guess is the right way to put it.
Everyone sort of converges on pretty much a similar recipe, essentially, to get the end result. As you say, you're limited on the boost pressure as well by the rules as well, correct?
Yes, yeah.
Okay, now in terms of the rest of that formula, twin turbo, again, a controlled turbocharger, which we'll dive into a little bit more in as we go on. Also, controlled fuel, which used to be methanol in IndyCar. Now they've moved to E85. When you're limited with the fuel and the octane that fuel provides, often this can get to a situation where knock kind of becomes the limiting factor. E85, I think in general, is a relatively knock-resistant fuel. So is that a concern in IndyCar? Is knock an issue?
I think in any racing engine, yeah, you're going to be concerned with knock. Over the years, Ilmor has gotten very good at optimizing the balance between knock and efficiency, is the right way to put it. So they're going to design the engine for efficiency first, I think is the right way to put it.
I guess this is probably a good place to maybe stop and define that term, because again, it's one that I know a lot of people maybe don't have a good understanding of. It's also a term that is often confused with pre-ignition, which is very different. There's also super knock. Can you get into the weeds with these terms? What are the three terms mean? How do they sort of relate to each other?
So actually, this is a funny subject because even in academia, the terms aren't very well defined. There's not like some some super, I think some people use the terms interchangeably. Some people use them different ways. So I don't think I'd ever tell someone that they're wrong. But generally, when we're talking about knock, with a traditional engine, like you're just trying to tune your knock sensor, you're talking about N-gas knock. So what's happening is you're going to light the spark plug, and it fires normally. So if you were looking at a cylinder pressure trace, cylinder pressure would shoot up after you fired it, but it would be smooth. Now what happens is that combustion mixture, so you can imagine you light it and it's like a sphere. It travels out from the spark plug. Now ahead of that sphere, the unburned fuel and air is compressing. So it just keeps getting compressed to a higher and higher pressure. And if it gets compressed enough, it's going to light, and that's N-gas knock. It's actually lighting ahead of the burn front that you created by lighting the spark plug. So now you have two separate burn fronts. You have a sphere ahead of your main one that you lit, and then when they collide, you can see that on your knock sensor, your cylinder pressure trace. You're gonna see the cylinder pressure get too high too quick, and you'll see a ringing. You'll essentially see a ringing where they hit. It's just a resonance that's created there.
You're talking about the collision between flame fronts. I'm interested to know then, there's a lot of engines, admittedly older ones, which were twin spark, which is essentially creating that same situation. So in those older engine designs with twin spark plugs and twin flame fronts, why do we not see that same sort of ringing, essentially, the issues we see with knock?
Generally, what's going on there is their combustion process is so slow that if you don't do that, your EGTs will be terrible. So essentially, you're limited on how early you can light it in terms of timing, because you'll still have an issue with peak cylinder pressure. But if you don't light it early enough, then your EGTs are super high because you're sending unburnt fuel out of the exhaust. So when they do two spark plugs, I guess kind of in theory, they are creating a actual pre-ignition event. It's just a controlled one. So they're trying to reduce the amount of time that it takes to burn all the fuel.
Okay, so coming back to knock in a modern engine, if we're looking at the in-cylinder pressure trace, we're seeing that initial sort of smooth, sharp rise in pressure, which is just the progression of the natural flame front and the fuel and air being consumed in the cylinder. And then we're going to see these sort of sharp spikes as we get these unburned pockets of fuel and air spontaneously combusting. Can you talk to us about what the effect, I guess, of knock is in terms of why is it damaging on the engine, and what is the failure mode that we see as a result of sustained detonation?
I think the obvious one is just your cylinder pressure can get very high. So these ringing peaks you'll see, you might have a small one, which, a lot of OEM engines will operate, even race engines will operate with a little bit of knock. You might see 1-2 bar. Like, so if you have an engine that's running 90 bar cylinder pressure, you get 1-2 bar of knock. It's not a huge deal, right? You don't want to run it like that all the time, but you're not going to break anything. It's when you get these 5-10 bar rises and knock suddenly, you can compress a ringland. You could destroy a rod bearing. You could, any of those things, take out a piston skirt on a cylinder wall, something like that. The problem with sustained knock, let's say you run 1-2 bar knock and you just keep doing it for a long period of time, you can have long-term damage to say a piston or a spark plug or a valve, because your heat's getting very high. Anytime you increase the pressure suddenly, it's a very sharp temperature rise. You might have something like the piston starts to anneal. So the aluminum of the piston might get really soft over time if you're just running it over its temperature limit over and over and over for a very long period of time. So there's essentially two failure modes. You have your instantaneous, your high pressure mode, and then you have, like a durability problem because of temperature.
The way I've had this described to me is that under normal combustion conditions, the crown of the piston and the cylinder head, for that matter, which are made out of aluminium with a lower melting point than the full heat of combustion, the reason these don't melt is because they're protected essentially by a thin boundary layer of gas. And one of the problems with sustained knock is it tends to essentially break through that boundary layer, allowing the full heat of combustion to reach the piston. So that's why we sort of tend to see a sandblasted appearance in the top of a piston that's maybe been subjected to continued sustained light detonation. Now, is that a good way of describing it, or is there another is there something else actually going on there that doesn't quite fit with that description?
Probably the way that you could describe it is the heat is burning things that maybe wouldn't burn. Maybe oil on the cylinder wall, maybe a coating that's on the piston. In my experience, I could be wrong, but I've never actually seen any kind of like gas layer on there. You do have unburned, you do have burned gas fraction. So in any, cylinder head design, you're going to have some exhaust gas that's going to stay inside the cylinder. And that does act as a damper. It's almost like a forced EGR. If you're very clever with valve timing, you can control that. But as far as a layer of gas protecting the piston, I've not experienced that in my job. The biggest thing that helps it out is if you cool stuff, right? So if you've got piston oil squirters, that is one of the best ways to make your engine knock resistant.
All right, so moving on from the discussion there on knock, we've then got what I'd describe as a very different type of abnormal combustion, which is pre-ignition. So can we get some clarity around what pre-ignition is and how it differs from knock?
So the way that I define that is you're essentially something else is playing spark plug. So you've got something inside the cylinder that's very hot and it's igniting the mixture before you light the spark plug. And that's obviously bad because it's like adding a bunch of ignition timing to your engine instantaneously.
So would this be maybe a hot spot on a combustion chamber, maybe a sharp edge or something that has ended up maybe glowing like an ember essentially during the last combustion phase, or is it something different?
Yeah, I tend to find that it's usually spark plugs. You usually just have a really hot spark plug. Obviously the temperature ranges refer to how far it is in the cylinder essentially. So if you've got a really hot spark plug, it can do that. I've seen it with exhaust valves, although if your cylinder head is designed correctly, the valve seat should cool the exhaust valve fast enough to prevent that. But if you've got a bad valve job or something, it can happen. And then, like you said, sharp edges, definitely, that's a problem.
Okay, so the failure mode as a result of pre-ignition, is that going to be similar to what we see with detonation? I mean, from my experience, a race engine will live with maybe moderate levels of detonation for a period of time, and you've kind of just defined the difference between how that might affect the actual cylinder pressure and why that's an issue. But let's put that aside. My experience, however, is with pre-ignition, particularly in very high specific output engines, is that you can essentially destroy a piston in a matter of a few engine cycles. So why is it that pre-ignition can be more damaging than knock?
Because you're essentially going to create a really, really exaggerated version of N-gas knock that we talked about earlier. You're going to have the pre-ignition light the mixture, but the spark plug is still going to fire. So it's almost like you've gone to a twin spark engine in an engine that was never designed for it. So the rise rate that you're going to have, like the time to like a CA50, like a 50% heat release, is going to be so fast that your piston will probably be right around top dead center. And then, the connecting rod has nowhere to go. It has no leverage on the crankshaft. So it's just, you got all this pressure pushing on something that's essentially, dead stops. Your piston's not moving. And it's like hitting the top of the piston with a big hammer.
The other aspect, as you mentioned there, the higher levels of heat. Is this one of the reasons why with pre-ignition, one of the failure modes we do tend to see is literally just a hole melted through the piston crown?
Yeah, exactly. Yep. Yeah, it's ideal gas law. PV equals MRT. If your pressure goes way up instantaneously and your mass is the same, your volume's the same, then your temperature obviously is going up in step. So yeah, you might see a peak change of 500, 700 C just because of pre-ignition.
All right, so we've talked about knock, we've talked about pre-ignition. Now, what about super knock, which is another term we hear? What's the sort of definition, or at least your definition of super knock, and how does that differ?
This is actually not a very well-defined term at all. So generally, someone who has an engine design like a Ford or an Ilmor or anyone, they're going to have a scale essentially of what they define as is trace knock. Sometimes you'll hear that referred to as borderline knock. You'll see tables sometimes in ECUs that'll have a borderline knock table. And what that is, that's essentially the limit of, okay, we're starting to see, like a quarter bar, half bar knock. Like it's just barely starting to knock. And then you'll have, essentially full knock. Like you'll have like a 5 or a 10 bar. Super knock with some manufacturers, they'll have a scale. They'll say, okay, at 10 bar knock, we're in super knock, right? Some engines, it might be 15 bar, we're in super knock. And the question you ask yourself is, why would you ever run the engine like that? And the answer is, if you design the engine correctly to use super knock, you can create extremely short burn times. You can make the engine essentially really, really efficient. It's very difficult to design an engine like that, but it can be done. And you're starting to see that in very high levels of motorsport, probably, most notably in F1. You're starting to see them explore the limits of what's possible with combustion, with their TGI system.
So if I can just come back and clarify that, just to make sure I've got the right handle on that. So you're almost purposely creating this super knock condition in order to get very, very fast burn times. Is that what you're sort of saying? In an engine, obviously, that's designed to support that level of combustion pressure?
Yes. I mean, or you might, super fast burn times and also very high cylinder pressure. So, the one nice thing about knock is, I guess nice is maybe the wrong word, but you do see very high cylinder pressures, right? So in theory, if you can use that, you should get very high torque levels because your cylinder pressure is going up.
I guess there's two facets to that. The cylinder pressure, yes, that's important, but it's not just the cylinder pressure that really plays into the torque being produced. It's also whereabouts in the engine cycle that peak cylinder pressure is being produced, because, sort of coming back to what you said before, if you're producing huge amounts of a cylinder pressure when the piston is absolutely at top dead center, well, that can't generate torque because it's forcing straight down on the connecting rod, which is in a straight line, correct? We need to sort of be a little bit past top dead center, so we've got that sort of that leverage working on the piston, then down through the connecting rod and finally into the crankshaft.
Yeah, exactly. You definitely want your peak cylinder pressure to be as late as possible, right? If you've got an engine that can only handle, 100 bar pressure right before it knocks, you'd rather have that 100 bar at 20 degrees after top dead center versus 10 degrees after top dead center, because you have more physical leverage. That's one of the big design focuses on modern OEM engines, like from the OEM side, because if you're limited on, say, 87 octane to a certain cylinder pressure before it knocks, you might work on your engine design and set it up just so that it happens later in the cycle. You see what I'm saying?
Yeah, sure. Now, so far through this conversation, you sort of inferred a number of times now that there's an advantage in getting the combustion process to be as short as possible. Is that what I'm picking up from what you've said? That's correct?
I think it depends. I think in general, it is nice to have it short because then you can move it wherever you need it to be. And if it's short, you can make it later in the cycle, for example, like we were just talking about, and not have to worry about your EGTs going nuts, right? There are exceptions, if you're trying to make it really, really fast at 2000 RPM on a regular, 2-liter engine that's in your Vauxhall or something like that, it's probably not good at that particular point. But if you're at 8,000 RPM and you're trying to make a big power number, it's a good thing.
And what, in general, does it sort of come back down to those same elements we've already talked about in terms of getting good mixture preparation and getting that near the spark plug that sort of helps drive what the combustion speed is going to be?
If you can get the mixture very, very even, what you're really looking for is you're looking for a consistent flame front. You don't want that flame front to encounter a pocket of extra rich or extra lean air. So you really want that to be a nice homogeneous mixture inside the combustion chamber. And also, like I said at the beginning, when we were talking about that Mercedes engine, ideally you'd have the spark plug in the center of your combustion chamber, and your combustion chamber would be a sphere, right? Because then you have the shortest distance between all points. That's kind of why you see small bore engines making a comeback in a lot of, even in performance cars. You look at McLarens, Ferraris, and the bore sizes have just drastically dropped. It's for that very reason. You want the physical distance to be as small as possible.
Yeah, that makes sense. Again, we're going off on a bit of a tangent, but it's interesting to me, hopefully interesting to some of the people listening. So I'll carry on. You just mentioned getting a nice even or homogeneous mixture in the cylinder so that you've got the ability to get a good burn speed, combustion speed. I don't know if they're still doing it. With direct injection, there was a range of engines which were purposely using the opposite at a stratified charge, where the design of the injector, the way it supplied the fuel, was sort of intended to give a variation in the air-fuel ratio throughout the combustion chamber. And my understanding of this was it's a lean burn process, and a lean air fuel ratio can be quite hard to light off or reliably ignite. So they would purposely try and get a richer kernel of fuel and air near the spark plug, which would light off, and then that flame front would be able to ignite the leaner air fuel ratio. What can you tell us about that? And is that a process that's still being utilized?
Yeah, you can definitely make it work. You can make it work in the lab, no problem. The issue is making it work over a huge operating range, right? So if you can mechanically design the system to say, create the ideal stratified charge at 3,000 RPM, that physical design of the engine is going to look a lot different than if you design it to make that at 6,000 RPM. So that's why, like F1, they went to that TJI setup. TGI is essentially stratified charge. What you're doing is you have a small pocket in that little pre-chamber that's rich or stoichiometric, something like that, and then it shoots into the rest of the combustion area, which is lean. So TGI is essentially just a mechanical stratified charge. I think if you could magically design an engine that did stratified charge at every RPM point, you'd probably be the richest combustion engineer on the planet. So
a work in progress.
Yeah, I mean, you can, like I said, you can do it. It's just a matter of getting it to work. I mean, if you need to start that engine in Norway in minus 20 C, but then somebody in Death Valley in the US runs it at 60 C, something like that. Yeah, it's just so hard to make it work over a huge range.
Yeah, absolutely. All right. As I said, we've sort of went off on a bit of a tangent, but let's get back to the conversation around engine design. And I mean, I'm interested not specifically on the Indycar engine, but it comes up because of your design constraints there. When we're looking at, let's take it away from Indy, so there's no sort of NDAs in our way, the relationship between our compression ratio, our boost pressure, and maybe the octane of the fuel we've got available. This is a question we are constantly seeing. What compression ratio should I run my engine on? So, what are the factors here? How much does a bump in our compression ratio, all other factors remaining equal, actually do to our engine efficiency, engine power and torque? Yeah, what can you tell us about that?
Compression's almost free power, right? Because it always creates a net gain in energy output from the engine. Obviously the problem with compression is that initial peak cylinder pressure spike when you first light the spark plug is going to be higher. That's how that's how you get that power gain, right? I think the way to consider it is think of boost and compression as the same thing, because you don't care that much what the actual compression number is. You care what the cylinder pressure is right before you light the spark plug. Okay. So saying I have 10-to-1 compression, I'm limited to 15 pounds of boost is simplistic. If your engine design's correct, you might be able to run 11-to-1 compression with 20 pounds of boost on 87 octane if you design the engine correctly. So I think thinking of it in terms of how much pressure do we have in the cylinder when we fire the spark plug is the correct way to look at it. I think compression's free power. Personally, if I were building my own aftermarket car, and I do, I love to build my own stuff in my garage at home. I go for compression first, and then I'll use the least amount of boost I have to, because you think about it, you got to have big compressors, you got to have a big intercooler, you got to have all these things. So from a practical standpoint, I think compression is a good thing within reason, obviously.
Okay. Yeah, I mean, obviously, as you mentioned there, it does need to be factored in with the fuel we've got available these days with, in the aftermarket, more and more people moving towards the likes of E85. How does that affect our choice, in terms of where we can go with our compression ratio?
So the nice thing about E85, it just has a bigger window. You can be off on the calibration and not hurt stuff, whereas gasoline is a lot more sensitive. It has a narrower range of where you can set it. So I think if you build something in the aftermarket and your plan is, okay, I'm always going to run this on E85, I think you definitely go for increased compression. I think some people get a little taken. Like, they'll take it too far with compression. They'll run pistons with domes. Don't ever run a piston with a dome. It's so bad for your combustion efficiency. And they'll do funny things with the combustion chamber. But I think within reason, you run as much compression as you can practically.
Let's just come back to that comment about domes. I mean, we work in a different world to yours, where we're not dealing with bespoke race engines that are designed from the ground up to do exactly what the designer wanted to do. We're dealing with a factory engine, and we're taking that engine and modifying it to achieve a different end aim. So, I mean, I can't think off the top of my head of any turbocharged factory engines where I've ever ended up with a dome. My old 4G63 drag engines were essentially a flat top piston, and that would sort of net us around maybe 10.5, 11 to 1 compression, depending on a few other elements. But if we take this to the naturally aspirated world, we're dealing at the moment with one of our project cars, which runs a K20 Honda engine. Really, really good in stock form, probably in my opinion, one of the best factory naturally aspirated engines anyway. Getting more compression into that, I mean, the dome on the piston is really the only way. Now, you mentioned that destroys or hurts your combustion efficiency. So what's it actually do? How does that play out?
I mean, there's a whole bunch of dynamics that go into that. When Honda designed that cylinder head, they never intended it to have a dome in the way of the airflow, essentially coming in when you're thinking about tumble, right? Or any type of charge motion. Now, depending on what fuel you're using, maybe the reduction in mixing efficiency is worth the trade-off. Maybe your power gain from compression offsets that. But if you think about it from the sphere example, when you put a dome inside that cylinder, now you don't look anything like a sphere. So ideally, you'd actually have a slight dish. You'd have like a spherical dish in the piston. And you see that in a lot of OEM engines now. They'll all have like these spherical dishes inside the piston top, because that creates a more spherical space. There's also a mechanical aspect to that. If you have a little bit more surface area in your piston, you have your cylinder pressure essentially has more stuff to work on. It's not quite linear because you have force vectors going in vertical directions, but I guess that works for a dome as well. But from a combustion efficiency standpoint, I would avoid running a dome if at all possible.
Okay. Yeah, that makes sense in terms of the sphere sort of example. I'm guessing in that case with a naturally aspirated engine where we wanted high compression, really the only way of getting that with a slight dish in the piston, therefore, is going to be a massive reduction or a significant reduction in the combustion chamber volume. And that really comes down into valve angles and everything else. Very difficult to do with a production cylinder head, but is that sort of the way you'd go with a bespoke race engine if you were to remain naturally aspirated?
Yeah, I mean, obviously there's always going to be compromises. Even in a race engine, you might end up with an oddly shaped piston just dictated by the rules of the racing class or something like that. But in an ideal world, you definitely keep the piston either flat or with a slight dish. Yeah.
Okay. Now, let's get back into the IndyCar side of things. So at the moment, as I understand it, there's two engine suppliers for the different teams. There's the Chevrolet Ilmor engine, and there's Honda Performance Development, HPD. I know we have to tread a fine line here because there are some commercial restraints on what we can talk about and what you can say. Obviously, one of the questions that's always going to crop up here is what sort of power are these engines producing? I know Ilmor want to keep that pretty close to their chest, as I'm sure do HPD, but could you let us know what is being quoted in the media in terms of approximately where the power level is for modern IndyCar engines?
I think the IndyCar website quotes something like, I think they quote like a 700 to 850 number or something like that, depending on the track. It does vary based upon track. So I think, if someone's interested in that, they look on the IndyCar website. It does quote an approximate power number. That's pretty much all I could say about that. But it does depend on track. It depends on setup. There's different setups. Like, for example, the Indy 500 engines aren't the same as the road course engines. There's some differences there.
Okay, can you elaborate a little bit on that?
It's just basically to keep them from going too fast at the Indy 500. They don't want them lapping at 260 miles an hour and killing a bunch of people.
Yeah, I guess there's got to be a sort of a happy sort of mid ground there. Because you mentioned that, the Indy 500, I guess that's an interesting challenge. I mean, not that any of the IndyCar races are going to be easy, but particularly when you go to these ovals and the Indy 500, you've got these cars lapping sort of circa 220 plus mile an hour. They're at or very close to wide open throttle, essentially barring incidents and pit stops for 500 miles. I mean, that sounds like a torturous task to keep that engine alive and healthy for that long. Can you give us some insight into the considerations that go into achieving that and how you prove the durability of the engine before you actually get to such a public event?
Yeah, I mean, with any durability program like that, you're obviously going to try and run it as hard or harder than it'll see in its actual use. So we're capable of doing full race simulations. There's also powertrain dynos that they can run the whole powertrain, for example, with the transmission and the differential as well. So you can do shift simulations because transients and things like that do matter. Without getting into too much detail, essentially, we're going to treat it worse than the driver ever will. And the idea is that if you get some ham-fisted driver who first season trying to show off to his team owner, he can't break it. And I think that when it comes to a race engine, the difference between what you do with, say, a drag car or even maybe like what an OEM engine would be is you're really looking at a thermal saturation standpoint. You're looking at a point where your engine coolant temperature has completely stabilized. Your oil temperature has completely stabilized. And most engines will never see that. So I think that's the big difference. On the one hand, it's kind of nice from an engineering standpoint because you know exactly where it's going to be the whole time. You're not dealing with some huge range of operation. But on the other hand, we run them, in racing, it's obviously going to be run really hot.
Yeah, I guess I'm assuming here as well that there's an element of the aerodynamics of the car. I mean, obviously, I'm going to guess here, getting maybe a little bit outside of your specific area of expertise. But I mean, obviously, you could control the engine coolant temperature or the oil temperature and bring that down simply by fitting larger coolers and ducting more air to them. But then there's the aerodynamic hit that the chassis is going to take from that. So a bit of a fine sort of tightrope you're walking on that front in terms of trying to minimize the aerodynamic drag on the chassis, but also keeping these operating temperatures within happy areas, happy mediums.
Yeah, for sure. You're exactly right. And that's not dictated by, the engine manufacturer. So it seems like, you're given not enough cooling and always asking for more power, right?
Yes. Yeah, perfect combination right there. In terms of the actual durability testing that you've mentioned there, and you sort of talked about doing a full race simulation. So we're talking here about, I believe they'd be referred to as a transient dyno. Is that correct?
We have a AC dyno, and we have another AC dyno actually being installed right now. And then we have 2 water brake dynos. So we will have 4 dynos in our facility. Then there's more dynos, obviously, in the UK. And there are some dynos located at GM that they use as well to evaluate things.
Can you expand on that AC versus a water brake dyno?
So, I mean, AC, it's just an electric motor. So using an electric motor to load things, it's much faster control. So if you can kind of think of, if I were going to hold the engine at 12,000 RPM, it can hold it to perfectly 12,000 RPM. With a water brake, if you ever use a water brake engine dyno, the control's not great. It's kind of moving all over the place. When it says 12,000, that's like throwing darts at a board. You'll get 12,300, whatever. So the AC dyno is really accurate, but it can also do much faster transient. So let's say you wanted to simulate a shift. You can have it go from 1 RPM to another RPM very, very quickly, because the electric motor itself is much more powerful than the engine you're testing. So it can just drag it down to whatever point you want. It's actually really cool. They're too expensive to be in the realm of like your average, even like a high-end build shop. You think of like your big aftermarket companies. Generally, they won't have an AC dyno because it's just an expensive thing. But boy, is it a nice tool when you've got one.
Yeah, it must be really nice to be able to do that full race simulation and just have the confidence in the components, which sort of leads me to the next element. I mean, obviously, one of the ways of making the engine more durable, more reliable is just by increasing the strength of the components inside it, maybe the crankshaft, the connecting rods, the piston, for example, which is nice in theory and might get the job done. But the trade-off is you're adding weight, which we don't want. So how do you kind of find the safety margin that you're prepared to run? Is this through these durability tests and actually literally breaking things and go, okay, we overcooked it there, guys. Let's add a little bit more material. Let's make it stronger. Or does this sort of start more in computer simulation before an engine's ever actually built for the first time?
Yeah, you're definitely going to start in simulation. It's so expensive to do prototypes and kind of iterate like that these days. You're going to do almost all of it in simulation now. And then dyno testing is just going to be to give you that last 10% maybe of confidence. They're very good now at doing this. For example, like you might use something like GT Power to develop, a combustion setup and sort of get like in-cylinder pressures, temperatures, exhaust temperatures, what turbocharger you need, these sort of things. And the correlation coefficients, we're at, modern technology, you can get to 95%. And they're so good, you can actually develop a VE table like for a speed density system and put it into an ECU on an engine that's literally never been run. There's none that exist, and it'll fire right up and run. It's pretty incredible.
So that's just the advances with the software and the computing processes or power that's allowed it to get to this level.
Yeah, also a lot of test data. So they have, after a while, you build up so much test data that you can kind of refine your model to match the actual test data from the past. So you eventually get so good at it that they don't need the mechanical engineers like me anymore.
You might be building yourself out of a job.
Yeah, maybe.
In terms of the engine's life, once it's sort of determined that the engine has run its useful life in race conditions, is it then a case of throwing it away and starting again, or do some of the core components such as the head castings and the cylinder block actually get reused?
We do rebuilds. Yeah, there will be rebuilds, both on all of our race engines, NASCAR, Indycar, all that kind of stuff. As far as what components get used, obviously there's going to be some very serious experts who are going to look into the materials and things like that to make sure, things aren't degraded. I do believe, I'm not 100% sure on this, so I may be off base, but I think we also have some rules about even if the part looks okay, we just age it out, where after a certain amount of time, you just don't risk it and you get rid of it after a certain amount of time. When you're dealing with an engine that expensive, you just you go a little above and beyond.
Yeah, absolutely. And I remember a few years back we visited Renvale in the UK, who make wiring harnesses for the likes of F1, WRC, maybe IndyCar. I'm not 100% sure. And they were telling us back, this was pre-cost cap days, but that they would replace the entire harness on the F1 cars after a race weekend just because it's a potential failure point. I don't know, as I say, cost cap may affect whether they still are doing that, but that's the sort of length these well-funded teams will go to. Anything that's going to be a potential failure point, you just don't want to obviously take that risk. Now, coming back, I should have probably mentioned this while we're talking about sort of knock pre-ignition, and you've kind of alluded to this already, the way you're monitoring this. I mean, for me in the aftermarket, I don't have the luxury of in-cylinder pressure monitoring. I'm using audio knock detection to physically listen to the engine, but you're using in-cylinder pressure transducers to physically see what that pressure is during each engine cycle?
Yes, during development, that's exactly what we do. It's just, I think if you're skilled, you can do a very good job with audio knock detection. And to be honest, when we do, if I'm going on site to do some testing, whether it be, on any type of engine, I will a lot of times hook up, a block mic just as kind of a sanity check. So I think that's a very, very good tool. But when you really want to get precise, when you really want to push the ragged edge, or you really want to develop the fuel efficiency of an engine or something like that, you need cylinder pressure data. And we use AVL Indycom. It's probably the most common one in the industry. So it'll spit out your CA30s, CA50s, AI50s, AI30s, all that kind of stuff. You can do a full PV diagram. So it'll essentially it'll analyze the whole cycle of the engine. So you can see your intake mean effective pressure and all that kind of stuff, which is really nice because sometimes the way the knock system works isn't completely intuitive, we found. So like a modern ECU will have a very, very sophisticated filtration system for like your knock detection signal. And setting that up is so difficult that you have to have, a cylinder pressure system.
Sure. Let's come back and just expand on a couple of those terms you've used, and you've mentioned it a couple of times through here, and I just want to sort of jump on it and get some more deeper explanation. You sort of mentioned AI50, CI50. Let's dive into what those terms actually mean.
CA50 is your heat release. So if you say CA30, that would be the crank angle at which 30% of the heat release of your fuel has essentially happened. And so CA50 would be where 50% is. AI is the same thing. It's just your mass burn fraction. So like AI50 is when half of the air and fuel mixture has burned. And the reason why we focus on that is you really care about where those numbers are in relation to where the crankshaft is. So you want to see what your essentially leverage angle, what we talked about earlier with the crankshaft. You want to see, is my lever arm 0? Is it a few millimeters? And that's kind of what you're working on to see, like, is my combustion efficient? Is it burning fast? Is it burning slow? That sort of thing.
So these are sort of key metrics that people at your level in engine design are really living and dying by, that unfortunately we just don't get to really understand or see in the aftermarket, correct?
There's a company called Kistler that makes something called a Kai box. It's a less advanced version of Indycom, and they're starting to get affordable enough that I think you'll start to see them trickle into like your more advanced aftermarket shops.
Yeah, definitely. I mean, I've been tuning now for 20 plus years, and at the start of my career, these were just 100% out of reach of anyone outside of OE or very high level professional race shops. And now, as you mentioned, that there are a handful of high end sort of enthusiast grade products. I mean, you're probably still talking, I think the one that I'm thinking here is the Plex in-cylinder combustion monitoring unit, and I mean, I think it sort of works out maybe $15,000 US. It's probably not something the average home enthusiast is going to jump on, but for those shops working in the performance aftermarket, that's probably affordable if you are doing some engine development, correct?
For sure. I mean, you think about it, if you're working on race engines, like If you save one race engine, you just paid for it, right? I mean, if it's 15 grand, that's really not bad. I think an IndyCom system is something like $100,000.
Yeah, there's a very, very big disconnect between these enthusiast grade products and the professional level stuff that you're working with, for sure. And we need to sort of understand that they're definitely still not going to be the same thing. Now, what I wanted to know is once you've sort of used the in-cylinder combustion monitoring, do you still retain that on the engine for race use, or are you using that then to maybe calibrate a conventional piezoelectric style donut knock sensor that's bolted to the block like we'd see on a production car, and rely on that for knock detection during the race and knock control strategies?
Yeah, for sure. You're gonna correlate the knock sensors to actual combustion pressure sensors. The problem with cylinder pressure sensors is, I mean, they've come a long way, but in general, they're kind of unreliable. You have to get them recalibrated a lot, and it's just even setting the parameters. Like if you were going to take a cylinder pressure signal and you were going to try and tell the ECU that this is the level that I want to start pulling ignition timing at, defining that level is difficult because the cylinder pressure signal is not that clean. So it would take a lot of post-processing. The cylinder pressure signal is very, very high speed. You're monitoring at a huge frequency, which again, I don't think you could make an ECU do that very well in a practical sense.
Yeah, sure. That makes sense. Just in terms of the practicality of getting these sensors inside the engine, again, the sort of enthusiast level product that I mentioned before, typically we'd see that installed as an instrumented spark plug, which is where the pressure transducer is actually kind of, I guess, for want of a better term, welded to the spark plug. So obviously that gives us access to the combustion chamber. Other options I've seen is where the sensor is directly fitted into the combustion chamber. Obviously a lot more complex around the location of water jackets, etc. Which of those techniques is used at that sort of professional level? Is the pros and cons with either?
I think you use the spark plug sensors when you can. It's definitely the way to go. It's so much easier to take in and out. They're more reliable. I think when you're doing initial development, like a base clean sheet design very early on, like of a cylinder head, you might put 2 or 3 probes inside, like directly instrument the cylinder head, because you might want to see pressure at different spots in the combustion chamber. But like for calibration, I think you're going to use the spark plug ones anytime you can.
All right. Let's move on, and I want to talk a little bit about boost control. And as I understand it, the IndyCar limitation at the moment, or control turbocharger, should say, is a pair of Borg Warner EFR 7163s, which is kind of interesting because this is probably one of those few areas where we in the aftermarket actually have access to essentially the same turbo technology. Now, we mentioned that the boost pressure is dependent on a number of factors, the track, etc. But from what I understand, around 1.5 bar gauge pressure, 22 psi, is that sort of in the ballpark?
Yeah, you're not far off.
They do, however, have the ability to run a push to pass with a slight increase in boost pressure. I mean, if I had access to that as a driver, I'd just be holding that button down the whole time. So I'm guessing there's some pretty stringent limitations on when that can be used and how many times or how long for. Can you give us some insight into that element?
Yeah, you're exactly right. You have limitations on how much you can use it, essentially. So the driver has to decide, am I going to use it in this spot? Am I going to save it for late in the race? That's actually more on the team side. So we obviously designed the engine to handle it, the increase in power, but how it's deployed is completely up to the team and the driver.
Okay. So there's a bit of strategy involved with that element of it.
Yeah, it's a huge amount of strategy. I think a lot of the drivers like to save it. That's what I've seen a little bit, kind of use it, last lap kind of thing. But, you just never know. Some drivers do their own thing.
Yeah, of course. In terms of the actual control of the boost pressure, are we still talking a conventional pneumatic wastegate? Is it electronic?
It's electronic, yeah. Mm-hmm. Yeah, it's an electronic setup controlled by the ECU for sure.
I'm guessing here as well there's sort of a really good incentive to make sure that you never exceed the boost pressure limit. So in terms of the governing body, how is that sort of mandated? How is that controlled? And what sort of slap on the wrist do you get if you happen to be a few millibars over that limit?
I actually don't know what the penalty is, but the governing body does have access to all of the engine data from the ECU. So they're going to, I would imagine it's a grid penalty. Like I said, I'm not trackside, so I don't know exactly how they would handle that.
No, fair enough. In terms of that trackside element, and again, you've obviously just mentioned that that's not what you're doing, but if you can give us some sort of insight as well, once the engines leave Ilmor, is there still an element of trackside manipulation on the calibration that's required, or is it just sealed, fit it, forget it, it is what it is?
No, the drivers have different preferences. So Ilmor will send a degreed engineer to every car that's got one of our engines in it, and they take care of ensuring the driver's happy. They can deal with any issues that come up at the track, and also calibration things. So as far as drivability goes, we refer to drivability as maybe how the engine responds when you come out of a corner. How sensitive is the throttle, things like that. Those are customizable to the individual driver's preferences. And, anyone who works in racing knows those drivers are kind of prima donnas when it comes to that stuff.
Yeah, some of them can definitely be a little bit sensitive and a little bit fussy. So I'm guessing what you're really referring to there is controlling the relationship between the driver's pedal position on the throttle and what the drive-by-wire throttle bodies are doing on the engine.
Yeah, for sure. I mean, there's a whole bunch of elements that you can control there, but you're essentially trying to make the driver as comfortable with the deployment of engine power as possible.
Okay. Now, I don't know if we can sort of dive into this at any level, whether it's a bit too sensitive, but obviously some of these longer races, fuel consumption is obviously a consideration, a major consideration. And there's a trade-off between the air-fuel ratio we run and the fuel consumption, clearly. Also, that plays into power that the engine can produce. Is this sort of something that's being considered and being taken into account with the calibrations as well?
Yeah, for sure. And the trackside guys will handle some of that on site because obviously, the way that a driver, uses the engine is going to affect some of this. So fuel economy is for sure a huge issue. The difference between winning and losing the race might be, avoiding one pit stop or even, getting the car to go one extra lap. It's happened in IndyCar before where a car will literally run out of fuel on the last lap, which isn't a good feeling. So
no, not so much.
Yeah. That I imagine that person didn't keep their job very long. So yeah, that's a huge consideration in all forms of modern racing. I think the way the sanctioning bodies structure the rules is they're trying to make it more relevant to normal OEM stuff, I think.
Speaking of that road relevance, from what I understand, there is an engine specification change coming about in the next couple of years. I think I don't remember the specific date, where IndyCar are going hybrid in much the same way as Formula One have. Can you give us any sort of input on how that's going to change things in terms of the internal combustion component of the engine design, or is it just really a carry on from where you currently are?
So they're changing the displacement rules. It's going to be a 2.4 liter V6 now. So not a huge change, but yeah, they keep changing it. I think the plan right now from the sanctioning body is to run them starting in 2024. But to be honest, originally the engines were supposed to be running next year and now they're not. So I'm not sure what the sanctioning body is actually doing on that side, but they've changed their mind several times.
I know I did read about some COVID-related supply chain issues, and I mean, anyone in this industry knows that we've definitely been facing our fair share of supply chain-related problems. I don't know if there's more to it than that. In terms of that change, right, increasing the engine displacement by 200 cc's, and then adding an electric element as well, is it safe to assume that we're expecting to see a reasonable bump in terms of outright engine power when we combine the internal combustion and EV elements?
Yeah, I mean, that's what the sanctioning body wants. I think they want to increase performance. Obviously, I don't have access to their brains, but I imagine the idea is to kind of close the gap a little to F1.
Yeah, I mean, it's two competing classes of open wheel racing, obviously quite significantly different rule sets. So yeah, both at the sort of cutting edge of their own classes. All right, look, I think we'll move towards wrapping this up anyway. We've gone a little bit long here, and I do want to be respectful of your time. So we'll move towards wrapping this up with the same three questions we ask all of our guests. And the first of these, DeWayne, is what's next and in the future for you?
Well, I mean, I think that my time at Ilmor hasn't been that long, so I imagine I'll be with them for quite some time. We didn't talk about it all in the podcast, but I also do my own stuff at home. I do like to play with cars just like you guys do. I've actually got, you guys are from New Zealand, aren't you?
We sure are.
Yeah, I've got a Dynapack 4000 in my home garage.
That's not a bad addition to the home garage. I actually used to have a Dynapack dyno, and it is a great piece of gear as long as you don't want to tune anything that's making really serious power, because the torque limits on those was always a bit of a frustration for me.
Yeah, for sure. I just do some open track days and like autocross stuff. I think you guys might call it Gymkhana, like the cone stuff. And so I've just got like a Mustang that's a track car, but me and my friends, we'll hang out and just dyno, whatever we find. So that's fun. So I do that. But yeah, I think Ilmor is for the foreseeable future where I'll be. I think as a company, they're treating me well, and it's very interesting. I've learned a lot since I've been there, and it's just cool to be part of a company that cares so much about excellence in racing.
I mean, you mentioned right at the start that working for the likes of Ilmor was the dream at the outset. So you've ticked that off. And I mean, the other thing with that is, where would you go to from Ilmor that would be a step up? You're kind of really at the upper echelon. So not maybe too many ways to move up from there, which is a problem, but a pretty good problem to have, I'm guessing.
Yeah, I mean, but there's a long way to fall, isn't there, if I mess up?
Absolutely. All right, our next question. What advice would you give, if any, to a younger version of yourself, maybe one of our enthusiasts listening, to maybe help fast track the career that you've already had, maybe avoid any pitfalls that you've come across?
I really wasn't that diligent with school when I was younger. I wish I would have tried a little bit harder with making sure that I did well in school, because you look at these places like Red Bull F1, you look at Mercedes F1, even a place like Ilmor, they all want to see someone who's educated and driven, and they really like to find people young. That's the best way to get into it. You start young, they groom you, and you can kind of move up. So I think if you're really interested in being serious about the racing world, listen to your mom, do your homework. It sucks, but it's the real deal. And when you're taking those thermodynamics classes and you go, when will I ever use this in my life? Well, if you go into race, this is when you'll use it.
Yeah, I mean, that's really great advice, and I wish I'd maybe taken a little bit more of that on board as well. I guess it's difficult when you are a bit younger, going through school, and everything else seems more inviting and enticing than knuckling down and actually putting in the hard work. I always think what I've seen in later years is it's much easier to be devoted and really knuckle down like that when there's that carrot at the end. You know what you're working towards, and maybe when you're still at high school, that's maybe not quite as apparent. But if anyone at that age is listening, take it from both of us, it will pay dividends. I think that's really solid advice. Last question for today, DeWayne. If people want to follow your journey, see what you're up to, maybe reach out, how are they best to do so?
I don't actually do much with social media, but I am on LinkedIn. So if you have a question about your career or you just want to know something, add me on LinkedIn, send me a message. I'd love to talk to a fellow enthusiast.
Perfect. All right. Thanks again for your time, DeWayne. Really appreciate all of the insight that you've given us today. It's been amazing to get that insight at the level you're working. So thanks so much. And we look forward to watching your progress in the future at Ilmor.
Yeah, I appreciate you guys having me on. It was a lot of fun. Thank you.
No problem. If you enjoyed this episode of Tuned In with DeWayne, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get more high quality guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt anywhere in the world. Also, this is a great place to ask any questions you might have too, and I'll do my best to answer them if your review gets picked. So this week, a big shout out to Giles Performance from the United States, who has said, "Great podcast. If you like the technical side of motorsports, this is the place. Possibly the only podcast and YouTube channel like it. Keep up the good work, Andre and HP Academy." Oh, thanks for the kind words there, Giles. And if you get in touch with your t-shirt size and shipping details, we'll fire a fresh tee straight out to you. All right, that concludes our interview. And before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now, remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our Gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a Gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.